Okay, I think we're going to go ahead and get started. So welcome to another session of Nano at Tech seminars here at IEN. Just a word about our next speaker on March 26th, 2 weeks from today. Our speaker will be Professor Vida Jamali from the School of Chemical and Biomolecular Engineering. So it's a pleasure to have with us today Professor Seung Jang from the School of Material Science and Engineering. Seung got his bachelor's, master's, and PhD all in material science engineering at Seoul National University. He then spent a few years at Samsung Electronics before doing a postdoc at Caltech, and then coming to Georgia Tech in 2007, where he is a professor in the School of Material Science and Engineering and also director of the Computational NanoBio Technology Laboratory. And so I will turn it over to you.
Yeah, thank you very much, David. So nice to meet you, everyone. My name is Seung Jang again. Today I brought a collection of the stories, and then originally I planned to give some very well organized, the one story to everyone, like energy. But later I felt like rather than just one story using computational methods for our research, I put some sort of more interesting stories in this PowerPoint file. Okay, so then rather than just computational nanobiotechnology, I would say computational nanobio energy and environment technology. So meaning that so nowadays we do everything, almost everything. So if you have any plan to make some collaboration with computational guy, so I would like to be one of the candidates in your list. Okay, so let's start. So multiscale modeling and simulation, that's the name of the method nowadays. So pretty much widely used, and then almost everyone knows what it is. Okay, so then next page may have picture for that, but before going there, wow, this is too loud. Yeah. So this picture, so definitely you know what it is. It's diamond, and then whenever we need to understand why diamond has such, the mechanical property or electrical or magnetic property, then normally what we do in material science and engineering is that we just get into the deep inside of the materials. So then you see only carbons. It is pure carbon allotrope, and then the connection between carbon atoms, it is sp3 bond chemically, and then also they have well-packed diamond cubic crystalline structure. So it is perfect 3D network structures. That's why it is so strong in mechanical point of view. And also the band gap is very wide because it is purely sp3. So that means it has a really large band gap, and then it is elucidator. Okay, but so then when we have such understanding, then so you can make next story like, okay, so if I want to make conducting diamond, then you can think about some doping into the system. And also if you think about some color, then nanoparticle could be embedded into the system. Okay, so diamond is the strongest material. Then how can you put some nanocrystal into the diamond, and then you open it and then put it and then close it up, then yeah, you can have some color. No, just kidding. So you need to make a grow. You need to make a growth of the diamond crystal in your lab. Then it is lab-grown diamond, so-called. And then there is no way to distinguish the lab-grown diamond from the natural diamond. If somebody claims, well, I can distinguish one of which one is what, then it's totally lie. Okay? Oh yeah, I mean there is one way. If it is very perfect, then it is lab-grown. Okay? If it has many defects, then it's naturally made diamond. Okay, so that's probably only one way we can distinguish a natural one from the lab-grown one. Okay, anyway, so now, we have principles, so experimentally, computationally, that principle is the same. And then we applied multiscale modeling and simulation approach. From the bottom, we use quantum mechanics, and then if you know what kind of element, what kind of atom, what atom type is used, in your material, then I would say we can make prediction, like a 70% accurate prediction, without knowing anything else, just knowing type of atoms in your material system. Okay? Metallic atoms, semiconducting atoms, or carbon or organic. So that's the story from the quantum mechanical study. And then, so now if you have interest for mechanical property, and then only one atom cannot give you such mechanical property. So then we need to have many atoms. What kind of computational method can you use? So then molecular dynamics simulation, which is from statistical mechanics, that is the method we can use. And also many times you could be interested in crack propagation or for some phase separation. If you think about, for example, oil-water separation, then oil phase, water phase, they separate from each other. So then to predict such phase behavior, so then you need to have even larger scale simulation tool, which is mesoscale simulation. Okay? So then, is that it? No, actually there is one more step, which is FEM. So probably you heard about COMSOL, Abacus, and such, really famous softwares. Those softwares are for FEM simulation, FEM calculation. Especially COMSOL is very interesting because it is multi-physics software, so you can do, mechanical property study and also the electrical properties, electromagnetic properties, study together from one system at the same time, simultaneously. So that's the sort of spectrum we have. So then, whatever property you are interested in, so you can pick one of them. But now, recently, it is more required to have some more holistic view of the materials, not just one of them entirely. So why? Because probably selection of the atom, choice of the atom was the reason why it had some phase behavior uniquely, and so on. So then, just directly just to tackle just one topic may not give you the really fundamental big picture. Okay, so that's why we do all of these multi-scale simulation nowadays. And then smart people nowadays, they put one more flavor on it, that's machine learning. Okay, but we just use machine learning in a very limited way to figure out what is the most important variable in your system. So we don't do fancy machine learning yet. Okay, but anyway, so that's the multi-scale modeling and simulation. And then story for organic material is the same story. Okay, same. Okay, so start from atom, mostly carbon, nitrogen, oxygen, fluorine type of sulfur type of atom types, and then so you make molecule or polymer, and then you put them together, and then they will form phases, and then a mechanical property or transport property, thermodynamic properties will be made from some large scale system. And then definitely coarse-grained mesoscale simulation or FEM must be desirable later. Okay, so then you can have some big picture. Okay, so then the topics in our group, so far some of them are done, some of them still going on, and then I will pick the sort of good pictures from each topic and put them together for this PowerPoint file. So that I wish you can enjoy it. Now, because of the nature of this presentation, it is not really, we don't dive into deep inside of each topic. I will just skim through each topic. So meaning that if you know some of these topics, then you will be glad. If some of the topics are new to you, unfamiliar, then you might have some puzzling things, then you may have some questions. So please feel free to raise your hand, and then we can talk, so very freely. Okay. So now, my background was polymer. And then during Caltech time as a postdoc, it was chemistry. Doesn't really have any limitation from material point of view. So organic or inorganic, metallic, semiconducting, all together, so-called hybrid material system was the the projects I had at the time. So, but again, the polymer was the starting point. And then whenever you have a chemical structure of the material, then bring it to me. Then I will make a three-dimensional structure. You will see some of them, bless you, some of them soon. And then we can do simulation for mechanical property. This one is a really basic one, stress strain curve, but all kinds of elastic or plastic deformation could be predicted and also interpreted. And then always, there is a next step. Once you have a mechanical property, then a next step is okay, so to make it stronger, what should I do? Double bond some of the bond. Out of these bonds, you can make a double bond, or you can put some chemical functional groups, and then you can think about those. But you can make experiment, definitely. But before doing experiment, you can do computations. Why? Because it saves time and energy. So manpower, money, so nowadays it is a big issue. So really important for your research. So then manpower, money, and also all kinds of material cost, so we can save them. Okay, it's very quick and accurate enough. Okay, so then phase behavior. This was the Monte Carlo simulation. So now, if you see the polymer, a molecule here, and then the gray color and black color, they don't like each other, so they would like to separate from each other. But they cannot run away from each other because they are chemically bound to each other. Then, if you put this type of a polymer or molecule into the system, high temperature, they were miscible because of the high thermal kinetic energy. But if you cool it down, then they separate as much as possible. Then they form the phase separation. Okay, this is the lamella structure. Why? Because it is a symmetric composition. Okay, and then you can think about, okay, so then if you keep this type of clear contrast, then a ring shape, cyclic shape, or H shape, whatever shape you think, so we can do simulation before your expensive experiment. Okay, so that is one thing. Okay, so then it was my very good opportunity, Nobel laureate in 2005 chemistry, the late Groves, Dr. Groves, he made catalyst. That catalyst was so good, and then he succeeded to make cyclic polymer. And then this cyclic polymer, definitely in the market, you can buy a cheap linear polymer too. And then, so we understand the linear polymer property a lot, but the cyclic polymer, so then does it have any different properties compared to linear polymer? So then this study was about viscosity. Okay? So if we have same molecular weight, same mass, then this cyclic new polymer has less viscosity, less sticky, simply. Okay, so and so on, and then the next step. Okay, not only the viscosity, phase behavior. If you put them together, linear polymer and the cyclic polymer, chemically they are the same. Then what would you say? If you put them together and then mix them and then just put it into the quiet place, and then will they make separation from each other, or they will stay together as a miscible material? Think about it. Okay, I will not let you know the answer right now, but think about it. So, but anyway, so that is a typical situation. Whatever we do, we have a question. If we know the answer, we do study still. Why is that? Because we would like to confirm our understanding is correct or not. Okay, but if we do not know the answer, we do study. Why? Because we do not know the answer. Okay, so either way, we do study. So this is just one good example about the material design. And then another material design example is this. This is amphiphilic molecule, which is a surfactant, which is soap molecule in your bathroom. So every day you use this, to wash your hands, or you do shower every day, right? Every day, right? So I do that, every day. But anyway, so now why do we need? Because surfactant molecule has really excellent performance between oil phase and water phase. Normally, dirty dirt on our hands or face, they are hydrophobic. and then just wash, just scrub your face, doesn't clean up, the things. So using this type of surfactant molecule together, then these surfactant molecule nicely sit between oil phase and water phase, and then reduce surface tension. Then dirts are easily, detached from our skin, and so on. So that's why we use this to investigate, this system, for what? Yeah, this is the current commercial product in the market, one of the commercial products, and then we use tons of them every day. And then they are going to ocean, okay? So then they are very, very stable in the nature and so on. You know the story. So then, we would like to use less amount of surfactant, less amount of soap, okay? Detergent in your dishwasher, okay? So then, one short tail, long tail there, and then is it the best? Okay, so then experimental friends, would suggest, okay, what about 2 long tails? Why it should be 2 long tails? How about 3 or 4 long tails? You can think about many things, but, are you sure that your design in your mind could be really, really valid, working well when you make it in your experimental lab? And so we need to have some confirmation somehow, and then before your experiment, I would say, so we can do simulations. Okay, so then here in this table, there's a summary of the numbers, simple numbers. Decane, one representative oil molecule, has experimental surface tension and water surface tension experimental value, and then our simulation value. So if you compare them, if they are not exactly same in terms of the each digit, but they are close enough. Okay, so then you can make this type. You can use this type of computational, study first before doing expensive experiment. That is another story. Okay, then another one. So let's be a little bit more serious. So this is a fuel cell study. So now this is the fuel cell scheme. Two electrodes, anode and cathode. We put an electrolyte between them, and then in fuel cell, especially a hydrogen fuel cell, the hydrogen gas is turning to proton, and then proton is moving through the membrane, and then they reach the cathode, and so then they make electricity. That's the most important part. Now, for the electrolyte, the naphthalene, commercial product naphthalene from DuPont has been used. It is expensive, more expensive than gold when they have same weight. Okay, it's very expensive material. So then, why not, to have replacement, a new material, cheap material. So that's the sort of one of the very important topics. Then hydrocarbon rather than fluorocarbon material it could be desirable. Okay, for many reasons. Okay, so we can make a cheap fuel cell car in the market nowadays. Winner is definitely battery car. So if we make some successful results, then probably you can see more fuel cell cars in the street in the near future. So, but anyway, so that's the story. And then to do this, we can make simulation, and then now you saw this type of proton hopping. This is the working mechanism in the fuel cell. Okay, through the electrolyte, there are waters, and then the waters are the media for proton jumping. Okay, you need water. Okay, so then, so whatever new material you think about, so your new material must have very good performance to facilitate that type of proton jumping through the electrolyte, through the system. Okay, so we do simulation again. So same story. So experiment. The cost is really not cheap. Okay, so then through collaboration, so we can accelerate the things. The machine learning is always another story. So then so once we have some good amount of data, then machine learning could work after that, because machine learning requires some good amount of data set. Okay? Right. We need to make a data set. Experiment is expensive. Okay? Right, so then, this is the one good picture at the electrode side, cathode side. It's a purple color is catalyst, and then there is water, as I said, is really important for jumping of the proton. And then the orange color here, those are O2 molecules. They are all together. What is the point? Point is that whatever you do in experiment, to mimic that experimental study, we needed to do complicated simulation. So many things are combined together, integrated together in one system. If you have experience about FEM, it is just, a black box. Like, okay, so you make a grid, and then in each grid you have some information. Where are they from? So handbook, yeah, okay, good. Experimental handbook, you can get some information, put it into your FEM calculation. Those values from a handbook, they are normally from bulk phase materials. Okay, if you have, big size, a big chunk of water or some metal, it has some property. Those values are from such large size material system. So here it is nanometer scale. So definitely in this room at the moment, almost everyone has a really good idea. When you reduce the size down to nanometer, then definitely the material property will be very different in many cases. Okay. So that's why we needed to have some information, and then our source here is computations, not just the random things, accurate, quantum mechanics based, also MD simulation based simulation data. Right. So then next thing is battery. The battery material, electrode, the electrolyte, so still going on. So this part is only electrode material. And then again, if you see somebody's picture here, so that is the experimental collaborator. So now, when we have the many different similar but different molecules or materials for electrode or electrolyte, again, so through our simulation, so we try to get some good value. Now here, experimental value and then our DFT simulation value compared. And then if you know the DFT, then you also know there are computational conditions. And then one of the most important condition is functionals. Functional, so function over functions. So that's functional. But PB0, all those, enigmatic, names are the name of the functional for DFT calculation. Now, when we use these different computational conditions, the results are a little bit different. These are voltage over your battery. Experimentally 3.1 volt, so now 2.9, 2.8. Wow, it is similar or different, depending on your impression. You can say something, but 2.6, 2.2, you see? They are very close. 0.1 volt, that's the uncertainty level nowadays we have. So if you try some new material, then let us do some computation. Then we can let you know about the prediction, which has 0.1 volt uncertainty. Okay? Right, so then this is another story for solar cell now. So solar cell, in this case, it is perovskite-based hybrid solar cell. So now the upper part and lower part, it is just, perovskite, the system, and then in between them, intentionally my collaborator put some spacer. Why? Because we already know the dimension of the perovskite, the size of the perovskite in nanometer scale, it determines the band gap. So for band gap engineering, so he made good samples, but he tried many different spacers between these two perovskite parts. Okay, so then depending on such choice, that we made good band gap calculations. So normally for DFT guys, and actually the size of the system you see here, it is not small size. Thanks to the supercomputers around us, it is now very much feasible and doable. But anyway, so it is not easy. Always, first we needed to have good structure prediction. Okay, good structure will give you correct property. If you have wrong structure, then whatever high-level computations you do, your properties will be wrong properties, which is garbage, normally we say. Okay, so yeah, so this is another one. And then as a function of the thickness, the band gap and also formation energy will be different. So that is a sort of normal thing we do. And then, yeah, this currently ongoing project for semiconducting polymer is this, actually, the Professor Stinsley in MSc department and also Antonio Facchetti in MSc department. They made good samples and then they tried to characterize the property. Again, in our side, in computational lab, so we try to make prediction. Okay, so when we use these chemicals as a building block and then make a polymer, and then so now the next question is, all right, what is the shape of the polymer chain, and then what is the three-dimensional packed structure, and then furthermore, what is the three-dimensional phase morphology? So those are really important. Why is that? Because as you know, as you might know, for semiconducting polymer, mostly the charge transport property is from the design of the chemicals. Conjugated structure is necessary, okay, in one chain. And then when we put them together, we put many chains together, then now the blue color, red color there, we need some phase, because not only through the backbone, polymer backbone, also between the polymers, there is a jumping of the charge. So to facilitate such things, we need good properties. So that's the topic we are working on. And then I will show you some interesting animations from our simulations. Now, another thing is that, yeah, such semiconducting polymer, normally it is brittle. It is very hard to make a process. It is very hard to make useful shape. Why is that? Because of that rigid, brittle character. So the mechanical property is very poor. And then you see, depending on design of the chemical structure, one of them is more stretchable, another one is non-stretchable. So then question is, if submitted to some journal and then referee quickly make this type of question. Okay, why? Why material A is more stretchable? Why material B is less stretchable? Definitely without computations, you can make some hand waving answer. Okay, so yeah, because of these reasons, yeah, polymer A, material A is more stretchable. But is it true? I mean, always we can make some rationalization, but when we have the question about is it really true or reason, and then definitely we needed some more backup. Like a computation is one of them, so definitely other experiment, many times it is required. So yeah, make long story short, this flexible, stretchable material has more degree of freedom of the torsion angle. Have you heard about torsion angle? In the backbone, dihedral torsion angle. If your background is chemistry, that is not difficult word. But anyway, so yeah, well, that's the sort of things. Now, I will show you a couple of more slides for that. So now, yeah, this is the conjugated polymer backbone for semiconducting property. And then it is rigid, useless. Okay, and then the smart people in experimental area, so they put what? Branch on the backbone. And then this branch is soft and flexible, and then make it processable first. Okay, then, yeah, it is processable, it's nice, and then your side chains, backbone, side chains, when we put them together, they quickly make what? Crystalline structure? Sometimes. But rather than crystalline structure, they make ordered structure. Okay, ordered structure. So if you have the textbook, please, grab it and open the crystalline part. Then crystalline phase, crystal structure has very clear-cut definition, meaning that this semiconducting polymer they do not satisfy such rigorous definition of the crystal structure. It has some order. It is not level, but it is not a level of crystalline structure. Okay, so order the structure. So then what happens? What's going on? That's the question. And then we put them together. It looks like very well defined at the beginning, but now we do simulation with some temperature condition. So now, yeah, this is the initial well-defined, well-packed structure, ordered structure. This is almost like crystalline, but it cannot be held. You know, it will be changed. Please see, this is the side view. Okay, stacked structure of the polymer is found here. You see? Very immediately, they will form some different structure. Okay, so now the backbones are here and here. Originally, it was what? It was flat. That's the initial structure, but very quickly, they make tilt structure. Okay, so through this stack of the backbone, still space through the space tunneling is possible. Okay, backbone through the backbone also possible, but the characteristics of the structure experimentally, the tilt angle was found very well. So we are very glad to have this type of good structure, which is comparable to experimental one in very good agreement. Okay. So that's that. And also not just here, not just there, also as a function of temperature, the volume expansion is found. You also know the volume is a function of temperature. High temperature, larger volume, low temperature, small volume, and so on, right? So then the volume is increased as a function of temperature, but now there is a big jump here. So then what happens, then through the simulation, the tilt angle at low temperature later. See? So now the backbone stack, between the backbone stacks, the space is increased. It is also well observed in X-ray analysis. And then also is found here. Okay, so then experimental value, this polymer, okay, found some peaks and then 370 around there. Yeah, so at the moment, we are still working on it, to characterize it more quantitatively. Okay, but it is going on, and then also the lower temperature. Later, we saw, first of all, we didn't see anything, but experimentally they found something around here at low temperature. Oh my gosh, yes, there should be something here around here. Why is that? Because these side chains, flexible side chains, they are what? Exactly identical molecule like oil. So if you think about oil property, if you have just only oil molecule, then they will be liquid in ambient condition. But if it is attached to this rigid, brittle backbone, then entropy is very much reduced. And then ambient condition, it is not really liquid. And then, so then you increase temperature a little bit more, then thermodynamically, so something will be happened at low temperature region. Experimentally, it is also found here. Okay, here you go. So 50 degree, around the 50 degree. And then we just investigated that area too. See? So again, so it is not completed yet. So we try to characterize it more completely at the moment, but it is very much promising at the moment. So thermodynamic behavior is thoroughly investigated. So through the backbone or through the space, tunneling or charge transport, that's the most important part. Fortunately, those informations are well studied already. Okay, so now the left thing is the thermodynamic behavior of this type of material. So that's that. Okay, the HOMO, LUMO, all those things are already done. Okay, then another interesting example, I believe, It is interesting. So Professor Frank in Stanford University, it was a long time ago, but anyway, so it was still very much, in my mind. Okay, so this is our human eye, and then outermost part is cornea. Cornea is a transparent part, just covering our lens. Okay, and then so if you feel tired, and then if you scrub your eye, then human cornea will be scratched a little bit, but it will be cured very quickly. Okay, but if somebody gets some injury and then not curable, then we need to put some artificial material. And then his project was, what kind of artificial material is good material to replace injured human cornea? And then that was definitely transparency required, and also oxygen permeation, because our eye always allow oxygen in and out. Okay, and so on. Then the candidate material PEO and PAA, those are tried, but they are too weak. Just they are just crushed in some stress condition. But in his lab, the graduate student found something interesting by accident. I have to be careful, by accident. That's my view. Okay, but they believe they designed it. But anyway, so now when they put them together, then you see this picture. It is very much intact before and after the stress condition. It's very strong. Same material, but independently weak, but when they put them together, very strong. So why is that? So stress strain curve also shows that sort of a mechanical improvement. And then at the beginning, we puzzled, and so we didn't know the answer at all. But later, so we did the simulation for mechanical property. Okay, so we just literally just expand it or deform it, and then during this deformation, all the molecular informations could be collected. Okay, the shape change and arrangement change, all those are observed, and then we try to analyze those changes. Okay, and then definitely now we know the answer, so that's why it was published. So topological constraint, that was the simple answer. Okay, but anyway, so if you have any material and which has very significant improvement, and then you look for the real reason, definitely you can do lots of experiment, but also you can ask me to do some simulation, and then we can work together. Okay. All right, so I will just jump on to other parts. This is bio application, NanoBio technology lab. So now this is bio part. At the beginning, it's probably Eric here. Eric may not remember this. So a long time ago, we had collaboration with the dental school in Augusta, and then the professor in dental school there, they brought some interesting but hard topic. If you have cavity, you go to dental office, and then you do what? You fill up that cavity using what? Filler. What kind of filler do you have in your mouth? So when I was young, gold was very popular. So everyone has some gold in their mouth, and then when they open their mouth, it is shining. At the time, it was not bad, but nowadays nobody wants gold, shining gold in their mouth. Aesthetically, it is not desirable. So people try to use white color, same color with our tooth, white color material, which is resin. Okay, curable resin. So the cavity could be filled up by those white color. The only problem is the orange color, this part in our tooth is dentin, which is very, 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 very hard collagen-based protein, okay, in our body, very hard collagen protein, okay, and then the interface, our artificial material, and then this collagen-based material, interface was very poor. Meaning that in the morning, you got some new feeling from dental office, but after dinner, you might lose it because it could be detached very quickly. So lifetime was very poor, and then the project was how to elongate lifetime, how to strengthen how to strengthen the interface between artificial material and natural dentin material in our tooth. So the story started from there, and then later they brought even more interesting story like, okay, so when we were baby, we don't have teeth, but later, teeth is generated, also bones. So it is so-called biomineralization. Only soft tissue was in the cell, but later we have hard inorganic material like minerals. So that's biomineralization. And then what is the fundamental mechanism for that? So we just checked. Originally, the story was positive and negative charge attraction. That was the reason. So calcium, potassium, all those ions could be attracted to the collagen because collagen has internal negative charge, and then through that positive and negative charge attraction could be the reason. That was widely accepted story, and then later we defeated it. Okay, so it is not true because even same charge was used, and they are still quickly get into the collagen. Okay, it is not charge attraction. Then it is what? It is osmosis based mechanism. Okay, so that's the story. And then so published well. Okay, so now we almost run out of time, so I will just show a little more the stories here. Another one is, again, bottom line is what? Computation can work with experiment. Okay, many times we make just publication out of only computation. For what? For computational method development. But when we tackle any topics in real world, then always we work with experimentalists together, okay, as much as possible. Okay, this is another story for that. Okay, so now another good opportunity for me was Professor Stodart's collaboration in Northwestern University, but at the time he was in UCLA, and then so now he made this complicated molecule, and then another professor in Caltech at the time, Jim Heath, and then make a device. Okay, and then the good point of this molecule is so it has a switching behavior. So here on off on off on off. It is very much reproducible, very stable, and then this material. So this is quick picture. So now blue ring here now stays on green part. It is electrically off state. Electron cannot go through. But when we move it to the red station, it is on state. It's switching on state. Okay, and then electron can go through this molecule. And then when it gets back, again, it is off state. So it could be repeated many, many times. And then the question is, why? Why this molecule has such switchable character? So the thing is that when we have the off and on state, normally, if you know the electronic structure of the material, so probably it is very well familiar to you. When we have energy level of electrons, then this type of moving part may not really affect the energy level of electrons. But strangely, this molecule has such behavior depending on position of the blue ring on top of green, on top of red. So the homo-lumo positions are significantly changed. So that's why we can see the switching behavior. Okay? So that was also very nice experience. So so that's why so we could make some good publications very quickly. That was another interesting story. Again, so if you deal with electronic structure of the material, that's another one. Okay, and then I will quickly. This is another collaboration. Another collaboration with Professor Ju in Cornell University. So now he made composite and then graphene flake or or carbon nanotube fragment. They put them together with polymers and then mix them, and then an interesting property was found. Low temperature conductivity is low or zero, But if you increase the temperature, conductivity is increased. Can you imagine? We know graphene or carbon nanotube, they are conducting. They could be conducting. But in the composite, low temperature, they are not conducting enough. But by increasing temperature, they are conducting. But cooling it down, again, non-conductive. So then what was the reason? And then also we solved this question. Okay. So then, for example, so these pictures, one graphene flake, and then, so now this one is two graphene flakes meet together, like this. So edge, and then plane contact, and then edge, contact, and plane contact. Many different combinations could be made in composite system, and then when they have decent contact, then we can get some charge transporter through the system. And then now, so to confirm that, we also used quantum mechanics and also the corresponding theory. But now, the contact is changed as a function of temperature. Then question is why? Why? So then these organic part in this composite, as a function of temperature, material always try to move, okay? Try to expand. And then expansion rate is different depending on material component in the system. Some of them, one of them is criminal, okay? Another guys are just a helper. Okay, so then because of that, some significant arrangement of the graphene could be made and then make new contact, and then reversibly it is again, get back to original state and so on. So that was the conclusion we found, and then it was published, okay, or so. Sorry, it is not accepted, it is published already. So not just accepted, it has page number type of things. Okay, so that is another very good and then another one is zinc oxide with a ZL Wang, and it was also 10 years ago round. So now this one, ZL Wang made zinc oxide, and then now in this case it is nanoplate, very thin. How thin? 6 or 7 nanometer thin, zinc oxide plate. So this is the TEM image, and then all of those, SEM image. Now you see how thin they are. Okay, so then what do you expect? When we have really thin zinc oxide semiconducting material, do you expect larger band gap or smaller band gap? So if we know quantum confinement, then we expect maybe it would have larger band gap. Okay, that's the general knowledge common knowledge we have. But strangely, you see, computationally first, we found it first. Okay, GL, so your material does not have band gap, and the GL didn't believe. Okay, so then please go ahead and then do some experiment to check what kind of band gap your nanoplate has, and then a photoluminescence and some other experiment, they confirm it is really conducting. Okay, so that was another sort of interesting story, through this collaboration. Okay. So nanoplate of zinc oxide is conducting. And then next question is always this, why? Okay? And then if you know the zinc oxide, if you make a nanoplate, always there is different two surfaces. Zinc on top and oxygen bottom, or oxygen on top, zinc bottom. There is no oxygen top, oxygen bottom, zinc top, zinc bottom. Okay? So then when they are far from each other, it's a big size, far from each other, they don't see each other. But when they are close enough, and then nano dimension, then they see each other and make interaction. So surface state of the electron is dominant, and then they make some conducting feature of this system, a conducting feature, in plane or out of plane, definitely out of plane. Okay. So then we will have some good amount of conductivity in perpendicular direction of the plate, okay, through this system. Yeah, so once we understand it, it's not that interesting, Okay, so then, so there are many things, but, I will just forward to show you just animation, couple of animation more. So now, yeah, so the guy in New York State, NYU, chemistry, and then he made complicated polymer like this, and then put it into water, and then they form together, spherical structures, and then now in our computations, see, these are TEM image, cryo-TEM images, and then from our, counterpart simulation, see? And so it is not just coincidence, so because of the composition and molecular design, so we capture the molecular interactions and then put them together in our simulation to predict accurate structure, okay? And then, so because of this agreement, we suggest some new polymer design. Oh, by the way, why do we do this? The reason is so when we have this type of micelle structure, and then the DOE project, this DOE project aim at the catalyst in the center. Okay, the catalyst is buried in the center. It is protected, and then yellow reactant get into the system like this, and then make a reaction, and then a product will be pushed away because of the high concentration accumulated inside. Okay, and so on. So that's the sort of a nano-scale reactor study. Okay, in DOE project. Okay, and so on. Oh yeah, so and then even switchable system could be made. Quickly make micelle like this. So inside hydrophobic, outside hydrophilic, and then we share the UV light, and then inside green color spiropyran, hydrophobic pyran, it becomes hydrophilic yellow color merocyanin, and then now it is yellow color. Can you see? One more time. Green color, UV irradiation, make yellow color, and then it is hydrophilic. It bursts out because it is hydrophilic, would like to make more contact with water. So imagine just put some hydrophobic cancer drug, whatever, into it, and then there's a targeting, it's a more accurate targeting possibly, and then not only light, also thermal energy could be used. Okay. Okay. So how many minutes? Like done, right? Couple of minutes. So this is another story with another professor in our MSc department, Faisal Alamjar. So now this is the graphene surface, and then we put platinum monolayer or bilayer. It is a very nice structure. And then I didn't believe at the beginning, when before I saw this type of high resolution TM image, I didn't believe this is possible because I know the graphene and the metal, they don't have a good interaction. I knew that. So I didn't believe it, but when he showed these pictures to me, and then, yeah, there's something I needed to understand. How come they make a good interaction, okay? And then, is it stable? Yes, it is stable. Then how come it is stable? Not just temporarily made and then quickly destroyed. No, it is stable. So we did the DFT study, and then we checked the binding energy and also the electron distribution, and then the application is, yeah, it has catalytic activity too. Okay, if we have oxygen, so then oxygen reduction reaction could be possible in catalyst, platinum side, and also make it upside down. And then carbon side also, it has oxygen reduction reaction activity too. Wow, so this could be, but the sad story is this platinum side or carbon side, the performance, catalytic performance is poor than just pure metallic platinum. So you don't use this for any current application. But maybe there is some application in the future, but more importantly now more important application of this system is the electron has a spin preference. Okay, so to make a chemical bond between platinum atom and graphene, it is really chemical bond. It is, where is it? Yeah, it is a really chemical bond between platinum and carbon in the graphene. So then because of that chemical bonding, the electrons in the platinum and also graphene, they have spins. So because of that, it has magnetic property, weirdly. And then because of that spin preference, so at the moment, we are thinking of application for spintronics or some optical response, weird optical response. So such things are still at the moment going on, okay, in this campus. Yeah, so this is the microwave-induced molecular motion, which could be used for selective heating. So you always do this in your kitchen using microwave. And then not only food, but also materials. So if you make some materials, many times you put some heat energy and cook it, right, in the manufacturing process. But how about microwave? So we can make a selective heating nicely. So, so those are here. So last story today, last part is this, quantum engineering material. So the,
Can you use the microphone?
oh, sorry. I'm so indulged in this. The quantum, normally we put quantum into some fundamental science field, right? Quantum mechanics, quantum physics, and so on, quantum tunneling, quantum entanglement. So are they really like useful for our applications for engineering? Yes. So that's the story nowadays in any universities. Okay, go any universities and try to figure out what's going on there for research. Then many of them are using quantum computing material for quantum computing, material for quantum sensing, and so on. So quantum thing is not just fundamental science, it is for engineering nowadays. Okay, so fundamentals are all known already, surprisingly. Okay, so then this silicon carbide system is one good candidate. Diamond is also good, but silicon carbide turns out it is more easy material to handle for spin coherence. Okay, so that's why. So spin coherence, what is the meaning of that? Up spin, down spin, we want to keep them for a while. For a while meaning that millisecond or microsecond is long enough. Okay, and then so we try to figure out such properties at the moment. Okay, so we just presented it in the APS meeting last week, and then at the moment we try to make manuscript for publication at the moment. Okay, so just the main topic is that so bulk phase well studied. How about nanoscale, like thin film, and then make a defect for spin generation in this silicon carbide, and then it has a long life, and then so what is the energy level, so and so on. So those are the stories I have. Okay, so probably I need to stop here, because so you guys are busy. So yeah, thank you very much for your attention. Any question, I will enjoy. Thank you.
Time for maybe one question.
No question is better. Oh, it's a question.
I'm not in this field, but always curious on your interest in research, how it's initiated. Is the experimental scientist find you to get the problem solved, or you get the results first and find people to prove your idea?
I see. So, both of them. Is normally in my research, agenda, some of them, because of my background, which is organic material and soft materials, and then I could have many ideas, and then I can start and then ask my colleagues, and then start our conversation. That is one part, and then another part, like 70% our research, my friends knock on my door and then explain their questions, and then we can start collaboration. So either way is just fine. Yeah. Okay. Thank you.
Professor Jang, one more time.
Thank you. Thank you.